Okay, so welcome to the session. So we'll have three talks. So first talk is given by Animesh. So Animesh will be talking about cosmological data from Pantheon. Animesh, please.
Yeah. So hi everyone. I am Animesh and I'm from TFR. So basically, I have worked on Pantheon Plus using an alternative statistical method. Yeah. So I have done this under the supervision of Dr. Mohammad Ramiz. Yeah. So basically, first I'll explain what type 1a supernovae are and how they are used as a cosmic distance ruler quickly. So basically, they are a class of supernovae which don't have any hydrogen line in their spectrum, but do have a silicon line, and they are a thermonuclear supernovae. And they have been of very historical importance, as we already know that they have established the evidence of dark energy. And yeah, so the progenitor of type 1a supernovae are believed to be a binary system of a normal star and a white dwarf. The white dwarf accretes the mass from the star. The white dwarf accretes the mass from the star, and when it exceeds the mass of Chandrasekhar limit, it explodes as a type 1a. So basically, they are termed as standard candles because the absolute magnitude for all the type 1a supernovae is same. And so knowing the apparent magnitude, we can know the luminosity distance to them. Basically, they are standardizable, not standard, because there's a scatter in their light curve. And fortunately, there has been an thing like empirical relation which can reduce this scatter, and which is termed as Phillips and trip correction. So what Phillips and trip correction is, like the width of the light curve, the days it takes to fall, is directly related to its maximum brightness, and there is a linear relationship, and it has been covered in this alpha x1 being the width, and also there is a color relation stating that the bluer the supernova is, the brighter it is, and it is also a linear relationship, and it has been given in this formula. So the software called Sol2, which takes in the supernovae light curves and spits out the magnitude x1 and c for all the supernovae, and gives us the finally standard candles. So basically, there's the recently released Pantheon Plus compilation of supernovae, and the data is publicly available. It contains about 1700 supernovae from 18 different surveys, and it is one of the largest supernova compilation. So basically, the Sol2 fitted table has already been provided, and it contains some of the previous supernovae from JLA and Pantheon. One notable advancement which has been made is the inclusion of many low redshift supernovae, and there is also an matrix with and the redshift range of this Pantheon Plus is from 0.01 to 0.001 to 2.3. So yeah, this is the sky map of the Pantheon Plus galactic sky map, which I made according to the surveys, and yeah, in the galactic coordinates. The redshift histogram for the Pantheon Plus, this is the survey-wise redshift histogram, while this is the general histogram. We see the importance here, like there are many type low Z supernovae here, as opposed to the previous compilation, which was a JLA compilation. So yeah, the peculiar velocity correction, I'll talk about quickly about the peculiar velocity correction for the Pantheon Plus and why it is important. So basically, the lower redshift supernovae have higher uncertainty contribution to the magnitude, like low redshift supernovae have higher uncertainty contribution to the magnitude, and also the bug flow corrections are done in the lower redshift. Previously, it had been pointed out that in the JLA, the redshift correction, the corrections were done till 0.06, and after that there were no corrections. But in Pantheon Plus, that has been improved by introducing a decaying function according to the ＬCDM model, and the y-axis here corresponds to the c value, which is the redshift in the heliocentric frame minus the Hubble diagram redshift, or basically the redshift in the cosmic microwave frame, and this is the redshift in the sun moving in the Milky Way. This figure has been taken from Colin et al, and this has been plotted for the Pantheon plus. Yeah, so the model I am taking, the distance modulus is given by the apparent magnitude minus the standardized absolute magnitude, which is given by this, as we had seen earlier. And from FIRW, we can calculate the luminosity distance to be this. Also, I have used the kinematic luminosity distance, which was the Taylor expanded luminosity distance, which was derived in this Matt-Wieser et al. And I have used both of them for my parameter estimation. The Q naught here is the deceleration parameter, and J naught being jerk parameter, and S being the snap parameter. Yeah, so the kinematic luminosity distance is basically a Taylor expanded luminosity distance. So it doesn't fit well at higher redshifts, and which we can see here. It is the this is the normal ΛCDM luminosity distance, while these are the Taylor expanded luminosity distance, and this is the range of Pantheon plus compilation, while this is the JLA compilation highest redshift. And we can see that for JLA, it was all right to use the luminosity distance, the Taylor expanded luminosity distance, since it agreed to about 95% order. But here, like the luminosity distance went, it's pretty far off from what the true luminosity distance is. So yeah, this was one thing to take into account. Yeah, so I'll explain the statistical model here. And so basically, I have used the statistical method, which was used in Nielsen, Kufanti, and Sarkar, and which was basically derived from which was the frequentist version of this Bayesian analysis, which used a Bayesian hierarchical model for supernovae analysis. And it generally states that the likelihood can be written in the form of the capped parameters are the parameters which we observe, and the theta being the model, and the likelihood can then be broken down into the MB x1 and c, given the true value of MB x1 and c, into the probability distribution of the MB x1 and M x1 and c, the M being the absolute magnitude. So yeah, the first term in this served as a statistical and systematic error, while the second term here is the model for M x1 and c, and the model taken for this M x1 and c is Gaussian, and it I have taken some Gaussian because simply this was the simplest version I could take. This can be improved upon by taking skewness and all those things, but yeah. So I have also assumed that x1, c, and m are independent. So the likelihood can be integrated finally to get this form of likelihood, and where sigma d is the statistical plus, where sigma d will be the statistical plus systematic covariance matrix, and sigma L will contain all those sigma m x1 and c parameters. Yeah, so fitting the likelihood simultaneously would give us the cosmological parameters along with the parameters for standardizing the supernovae. Yeah, so I estimated the parameters, and I got like for omega m and omega lambda, I didn't use flat lambda CDM for this, but I got this value. And the Hubble diagram I have plotted in here. Yeah, I also did this for the Taylor expanded luminosity distance of order 3 and order 4, and got the parameters. Like the estimated parameters don't have any meaning without placing the confidence interval in them. So I used Wilks theorem to place the confidence interval, and for this I use the profile likelihood, and I varied omega m and omega lambda over a 2D grid from 0 to 1, and use a spline to get the profile likelihood. and using the Wilks theorem on the test statistic -2 log L eta or L theta, which is chi-square distributed with 2 degrees of freedom, I get the 1 sigma, 2 sigma, and 3 sigma confidence ellipsoids. And yeah, so the thing with this is like the estimated parameter was this, and I got these confidence ellipsoids. This is like a pretty far off from the current ΛCDM, but it okay, it is last slide. Yeah, so it is far off from the ΛCDM, but it agrees upon with the original paper which originally used this analysis, and they also got the similar kind of results. And yeah, so basically what I wanted to say was that the conclusion with this holds, and they had used the JLA analysis. I have used the Pantheon plus. Further on, I'm improving with adding skewness on the distribution of ellipse correction, and adding the components to the covariance matrix. And finally, I'll try to analyze the data similar to this Collin et al. Paper, and I'm working on LSST pipelines. Yeah, that is all.
Any comment? Questions? Okay, yes.
Your analysis is consistent with a very low omega m.
Yeah.
Would you like to comment on, omega m measurements from perturbations, CMB, large scale structure?
Actually, like I can't comment on those because like I haven't actually done the CMB analysis and all. But
do you think it has to do with systematics in the supernova data?
There is a thing like I haven't included the model isn't truly Gaussian, and the covariance matrix which I have used, the covariance matrix provided was a n cross n matrix, and I had converted into a 3n cross 3n matrix with some of the elements being 0. So yeah, we can input some of the more covariance elements to get a better result. Yeah, so this analysis itself won't be a like conclusive proof of something, but yeah, it can be improved upon further, and it's just an alternative method, which was like.
Yes, yes, sir.
What's the value of H0 you get out of this analysis?
I don't get any value of H0. I just put the value of H0 to be 70.
70. Why?
There is no like
I know of two values, 67 and 73. So why 70?
Kind of in between.
Oh, average.
Yeah.
So just yesterday, one paper arrived in the appeared in the archive, and they have used this Pantheon 2 data, and means they have used a different kind of statistical analysis, and they have shown that the value of H0 it actually is they claim that it has reduced by 40%, so they get the value around 70. It appeared just yesterday.
Yeah, so I didn't take that into account.
No. They have showed that the data that he have, the Pantheon plus, they use basically the Gaussian likelihood, but they said that the likelihood may not be Gaussian. It can be a T distribution or I think the other distribution I forgot, but what they showed that if you take that thing, the error were reduced by 40%, not the value.
Thank you.
So thank you very much.